All right, in this video, we're going to go over Module 8, Lesson 1, which is kind of basically our introduction to exponential functions. So Module 8, Lesson 1 is talking about exponential functions, and we have given a mathematical or real-world context, we're going to classify an exponential function as representing growth or decay. So that is one of the benchmarks we will be covering today. An exponential function is a function in the form of f of x is equal to a times b to the power of x, where a cannot equal 0, because if a was equal to 0, then everything would just be equal to 0, because we're just multiplying. B, our b term, must be greater than 0, so that means it cannot be negative. And b also cannot be equal to 1, and b can't be equal to 1 because 1 to any power is just 1, so that doesn't work either. So kind of a lot of restrictions on exponential functions as far as what an a and b can equal. Exponential functions are nonlinear and do not have a constant rate of change. So let's look at parts of an exponential function. We have our f of x, which is a fancy way of writing our y value. Our y values is also talking about our outputs. Okay, the a term of our exponential function is our y-intercept. It is an implied 1 if there is no number listed. So we'll see an example of that here in just a moment. Our b term, that is our ratio. That is how our exponential function is either growing or decaying. And then we have x. Oh, and of course, I already mentioned it up here, but b cannot be negative, okay? B must be greater than 0. So then we have our x, and our x is our exponent. Okay, our exponent is the variable here. I know you're used to having your variable down here as the larger numbers are your base, but now our exponent, our variable is the exponent, and that is the input or what is changing in our function. So sometimes you will see it written, an exponential function written in this format. So almost everything is exactly the same. We have our y-intercept for our a. If we are adding something to 1, that would then make this whole parentheses greater than 1, so that would be showing growth. If we are subtracting something from 1, then that would be our b term, what's in the parentheses, is going to be between 0 and 1, so that would show exponential decay. The x is still talking about the exponent, and then we have this r, which we didn't have an r over here, but what the r is talking about is the rate. So how is something changing? And again, it relates to 1. So either we're going to take that rate away from 1 or we're going to add it to 1, and that will tell us if it's growth or decay. There are a lot of real-life examples for exponential functions, and they include pandemics or the flu or a virus or a cold even. Population, okay? Population and how it's growing is an example of exponential functions. Compound interest. Ask your parents about compound interest. If they have a bank account or even a credit card account, you can earn or lose money compoundingly with compound interest. And then we have depreciation. Depreciation, an example of that would be buying a brand new car. As soon as you drive it off the lot, the value of that car has decreased. So it's depreciating at an exponential rate. Okay. With exponential functions, we have this thing called an asymptote. Very funny word, but what an asymptote is it's a line or an imaginary line. It is not a line that you will see that a graphed function will approach, but never, ever, never, ever, never, ever, never touches. Okay. So here we have our exponential functions, and that is when b is greater than 1, or you could see it as a multiplied by 1 plus r, because 1 plus something is going to be greater than 1 to the power of x. An example of that type of function is f of x is equal to 2 times x. So this could be written just like this, and the reason why this is important is because there, again, is an implied 1 You will not see it in the function, but you have to remember that that 1 is there, because that 1 that's in front of that 2 is telling us our a term, or most importantly, our y-intercept. So you'll see it listed here in the table as 0, 1, because remember, our y-intercept is always when x is equal to 0. So that is this point on the graph, and I can list it here under my key features as my y-intercept being 0, 1. So my b, my ratio for this exponential function, is equal to 2. Okay, I can see that here or here. 2 is greater than 1, so that is why I am showing exponential growth. And you can see here in a graph, if I'm reading this from left to right, it is increasing. If I'm looking at my x values either in my table or in my graph, I can see that my x values are increasing. And if I look at my y values on the graph or in the table, you'll see that they are also increasing. So these are going up, these are going up. So both my x and my y values are increasing, which is telling me this is a growth exponential function. The asymptote is this imaginary line. I just highlighted the x-axis, and that is where y is equal to 0. So that is the line that the function will approach but will never ever cross. Then we have our domain, and our domain is all of our possible x values. Well, all of the possible x values go on and on and on for infinity. So we are going to give that a symbol of an R, or two I's with an R in front of it, and that stands for all real numbers. And yes, I know you are thinking, but aren't all numbers real? No, there are some imaginary numbers, and you'll get to that in your higher level math. Then we have our range, and our range is talking about all of our y values of a function. So our range is always going to relate to our asymptote. And here, because our asymptote is y is equal to 0, the range for our exponential function is going to be y is greater than 0. Any value, any y that is greater than 0, so 0 0.1, 0 0.2, 0 0.0001, those are all possible y values in my function. All right, so let's talk about exponential decay. Exponential decay is when b is between 0 and 1. Sorry, that's supposed to be scooted up. It can also be written as a times 1 minus r to the power of x, because if I'm taking something away from 1, then it's going to be between 0 and 1. Okay, an example of this would be 0.25 or 1/2. All right, so the function we are going to graph is now f of x is equal to 1/2 to the power of x. So if I'm looking here, I am going to remember that I have an implied 1 for my a term. So a is equal to 1. So that here on my table, you can see is 0 and 1. And here on my graph, 0, 1. And so I can label that under my key features. My b, my ratio here, is 1/2. And I can see that my b is 1/2, and what it looks like on my graph is that it's decreasing, or kind of looks like I'm on a slide. I'm sliding down a hill. If I'm up here on the top and I'm going from left to right, I'm sliding down this hill. And so that function is decreasing from left to right. So what that means is here my x values are increasing. You'll see it here in the table, -2 to -1 to 0 to 1. Those x values are increasing. But what is happening to my y values? I went from 4 to 2 to 1 to 0.5. My y values are decreasing. So this is an exponential decay function. Now let's take a look at the asymptote. Again, that's the imaginary line right here. And it is still going to be 0 because it is approaching the x-axis, but will never touch the x-axis. Our domain here will be the same as it was before, all real numbers. And my range will be anything greater than 0. Again, the range relates to the asymptote. All right, so let's take a look at what it means to graph, or how we can graph this function. And I like to use a table to graph my functions because you can use a table to graph a linear function, an exponential function, or a quadratic function. So first thing we're going to start with is our a term, our y-intercept. So our y-intercept for this function is 4. A is equal to 4. Here in my table, my x value is 0. My y value, I'm willing to bet, is going to be 4. Because I bring this 2 to the 0 power, well, anything to the 0 power becomes 1. 4 times 1 is equal to 4. So I put that point on the graph. Notice that these vertices are going up by 2. So this is 2, this is 4, so this is the point 0, 4. I can also label my y-intercept as 0, 4. Now I'm going to go ahead and take a look at my ratio of 2. Okay, so my b is equal to 2. It's increasing by a ratio of 2, which means I have exponential growth because 2 is greater than 0. So now how do I graph another point? Well, if I'm plugging in -2 for my x, I have 4 times 2 to the power of -2. I replace the x with the -2. So that simplifies to be 4 multiplied by 1 over 2 squared. Remember, I had to get rid of that negative exponent. And that is equal to 4 times the 1/4 power. So that is equal to 1. So I graph my point at -2, 1. -1, -2. I'm going to estimate as 1 being halfway in between. Now I'm going to graph my next point. I'm going to continue to find these values by plugging in an x, or plugging in an x value from my table to find my y value, my output value. All right, so now I have all of my points plotted. And now I'm going to connect the dots and finish identifying my key features. So if you look here, either at the table or at the graph, as my x values are increasing, okay, what is happening with my y values? So notice my y values here are increasing by a ratio of 2, or being multiplied by 2 each time. So as my x values increase, my y values are also increasing, which confirms my growth assumption. And my asymptote here is still my x-axis. So my y is equal to 0. The domain, all of the possible x values, is all real numbers. And the range, again, relates to my asymptote, is going to be any y value that is greater than 0. All right, moving on to the last graph. We're going to graph the function f of x is equal to 2 times 1 minus 0.5. If you have a 2 here in the parentheses, please write over it, white it out, cross it out, whatever you need to, and put a 1 there. That was a typo. There should be a 1 here, not a 2. Anyways, 2 times 1 minus 0.5 to the power of x. So I would plug that all into a calculator to find my y value after I identify my y-intercept. So my a term here is 2. A is equal to 2. Here it is on my graph, is when x is equal to 0. Okay, remember my y-intercept is always when x is equal to 0. Here I'm just showing you the math of what happens with anything that's to the 0 power, just becomes 1, which is why our a term is our y-intercept. So I plot the point right here on my graph. Again, I'm going up by 2's, so be careful. Put the point right here next to the 2. And that's the point 0, 2, my y-intercept. Now I'm going to look at this. My b is 0.5. And I know that because I'm subtracting that 0.5 from 1. And 1 minus 0.5 is 0.5. So it's decreasing by a ratio of 0.5, which is showing me exponential decay.